All right, example 6, power form. These are the stranger indeterminate forms. 0 to 0, infinity to 0, 1 to the infinity. So to do these, we're going to be using logarithms. So the big factor we're going to use in both of these problems is the fact that e to the x and natural log of x are inverses. And because they are inverses, we are able to do some pretty funky, cool things with it. For instance, I can write the number 2 as e to the natural log of 2. Because since e and ln are inverses, they just cancel each other out, and we're left with the argument, what was inputted. So in general, we can always take some function and write it as e to the natural log of that function. Or the other way around, we could also write this as natural log of e to the f of x. That also works. But we're primarily going to use this form. We're going to do e then the natural log, because the natural log allows us some really nice things. Like for instance, let's remember here, for properties of logarithms, the natural log of a raised to some power p is just p times the natural log of a. And it's this property right here that allows us to take an exponent and extract it. That's what's going to give us some simplification power in these examples. So let's get started with part A. So for part A, we're going to go ahead and say that x to the x squared is none other than e to the natural log of x to the x squared, which then simplifies into e to the x squared times the natural log of x. And one thing that we also learned, which I guess I can put up here as well, all up here, is a limit law. So if a function f is continuous, then the limit, as let's say x goes to c, some value, it doesn't matter, then the limit of f of g of x, so we've got some composition of functions, one function inside of another. This is the same thing as f of the limit as x goes to c of g of x. In other words, we can pass the limit through the continuous function, and we can just evaluate the limit of the interior function, because limits are unchanged by continuous functions. So continuous functions preserve limits in a sense. So notice down here that that's exactly what we have. We have e to the x as our outside function, and our g of x here, so this would be our f of x, our outside function. Our inside function here would just be x squared ln x. So we know that e is continuous. So since e is continuous, we know that the limit as x goes to 0 from the right of x to the x squared, which is equal to, actually, let's go ahead and replace this, right? We know that this is the same as this, so let's go ahead and write that. This has to be the same thing as as e to the limit as x goes to 0 from the right of x squared ln x. So we really just need to evaluate this limit. And if we know this limit, we'll then just take e to whatever that answer is, and that is going to be the answer to this limit. So we don't have to carry around this clunky notation. Let's just examine that inside limit directly. So as written like this is of indeterminate form 0 times, again, natural log technically, as you go to 0 from the right, goes to negative infinity, so this is technically 0 times negative infinity, but we're not going to care or make a huge distinction with that. This is really just a clue to us that we should go ahead and rewrite this. So we'll go ahead and rewrite this by placing the x squared in the denominator by writing it as 1 over x squared in the denominator. Now, reassessing the form, this is infinity over infinity. Okay, which now means that L'Hopital's rule is a valid option for us. So if we use L'Hopital's rule, the derivative of natural log of x is 1 over x. The derivative of 1 over x squared is negative 2 over x cubed. And now here we've got a fraction divided by another fraction, which we know is just multiplication by the reciprocal. So this is really 1 over x times negative x cubed over 2, which is negative x squared over 2. So the limit, as x goes to 0 from the right, we can factor out the negative. That just makes it look nicer. X squared over 2. All right, well, x squared over 2 is continuous at x equals 0, so this is negative 0, which is just 0. Now you got to be careful. It is tempting to say, I'm done, and move on, but we really only determined this limit, and we know that the answer to this limit, the actual problem that was posed, is e to our answer. So this means, therefore, the limit as x goes to 0 from the right of x to the x squared is just e to the 0, which is 1. Very similar train of thought for part B. So we can say that x over x plus 1 to the x is equal to e to the natural log of x over x plus 1 to the x, which is then e to the x ln x over x plus 1. And the limit as x goes to, where are we going, infinity? Okay, we're going to infinity of this e to the x ln x over x plus 1 is exactly the same thing as e to the limit as x goes to infinity of x ln x over x plus 1. Just like before. So with that, we can then just examine this limit, get the answer, and then raise e to whatever that answer is to this limit. So, proceeding, we have the limit as x goes to infinity of x ln x over x plus 1. This would be of indeterminate form infinity. Natural log is continuous, so if we take the limit inside here, the limit of x over x plus 1 as x goes to infinity is 1, and the natural log of 1 is 0, so this is infinity times 0, which again, can't use L'Hopital's rule on that directly, but it is a clue to us that if we rewrite this, we should be able to use L'Hopital's rule. So rewriting by dropping the x into the denominator, rewriting it as 1 over x, reassessing the form, we do have 0 over 0. So now, applying L'Hopital's rule to this expression, derivative here is going to be fun. Let's just lower this a little bit. So remember that when you take the derivative of the natural log of some function, this is just the derivative of the function on the inside divided by the function. This is just the chain rule applied to natural log specifically. So because the inside is a fraction, if I divide by that fraction, it's really just multiplication by the reciprocal. So I can go ahead and say 1 over the inside is going to be just the reciprocal of the inside times the derivative of the inside, which now I've got to use quotient rule for, which means my fraction should probably get a little bit bigger. So the derivative of, we're differentiating the inside here of the log. So the derivative of that the top of that inside is 1 times the bottom left alone. minus the top times the derivative of the bottom, which is 1, all over the bottom squared. Guess we didn't need as big of a fraction as I thought. All over derivative of the bottom, which is negative 1 over x squared. Now this looks absolutely terrible, but we can clean some things up a little bit. Notice these x's cancel, and one of these factors cancel, so we just have an exponent of 1. So the top really is 1 over x times x plus 1, divided by this fraction. So when we divide by this fraction, let's just move that negative all the way out front. So there's a negative, and if we're dividing by a fraction, this is really multiplication by the reciprocal. So we really have 1 over x times x plus 1 times x squared over 1. Simplifying this, of course, we can cancel this x with one of these, and then we're left over with the limit, negative the limit, as x goes to infinity of x over x plus 1, which is, by dominating terms, 1, but times that negative, we end up getting negative 1. So, therefore, the limit, as x goes to infinity, of x over x plus 1 to the x is equal to e to the negative 1, which we can just keep that as e to the negative 1, but I like writing as a fraction. That doesn't matter really, but it is 1 over e.